Today I worked on a new lab by Codewars.com. This is QU5, and it's about cryptography using Cipher ciphers, such that we are using a class called Cipher cipher, and the cipher algorithm is such that we will be using the uppercase letters in the alphabet, and we will be shifting each character by the shift count given in the problem definition. It can be shift of 5, shift of 3, whatever. And we will find the new corresponding uppercase letter and return that. So this is how we will be working on with this cipher. It will go two ways. We will use it to encode and decode basically. So in this class, the only attribute we have here is shift. So it is self.shift, and using the convention we call the shift for assigning the attributes to the objects, and the object is the cipher here. So start with, we need to also give the alphabet. I will call it self.a, English alphabet, uppercase letters. I'll just copy it and paste it here. So all the way from A to Z. Now I need to generate the cipher. I call it S. And again, that's based on the rule that we will be shifting the letters, the characters, by the shift number given here and return. So to do that, I start with an empty string. And what I will do is I will call the characters in this self A. So for I in, and I need the index numbers because I will do mathematical operations. So instead of getting them directly as for I in self A, I will be using range length of self A to be able to use the index numbers properly. All right. What I will do is I will define a parameter called count, and this count will be the number of the index number of the character in the English alphabet shifted by the shifting number here, by the shift. So it will be the index number I. Here's index number, and I will add the shift number. So I will put in self.shift. I'll add that. Now, if I do that, the problem that I will be facing is that this I plus self shift count will go beyond 26. So my for loop will be looking for elements with index numbers higher than the upper bound of 26. Right? So to bypass that, what I can do is I can put in parentheses. I can do this modular operation such that I will change the numbers to mode 26 in that case. So what I mean by that, I worked it out here for a quick example. So let's call this index, and let's call it n. And here, let's say n is 9. So n9 means we have 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. So their index numbers are 1, 2, 3, 4, 5. So if I do, I may look for index up to 5. If I do n modulo 5, what I do is I will do this operation means that I will take the n and divide it by 5 and report the remainder, right? So if you do this operation on 6, the remainder will be 1. So for 7 will be 2. So everything will be shifted over here. In other words, these two numbers will have the same index number of 1. These two numbers will have same index number of 2. So originally this number has an index number 6, but with this operation, reporting it as a reminder, I'm changing index number to 1. So by doing that, I'm making sure that all the counts are within or are equal to or less than the upper bound of the range in this problem defined as 26. Right? Once I do that, I can take this empty string cipher self s, and I will append the letters in the English alphabet with count as the index number. No. There are alternative ways to do it, of course, but that is the way I did that, and I think it works. Now, in order to define the encoding and decoding functions, I need to be using this translate and make trans methods. So I try to address them over here. So translate and make trans. These are really the two methods I will be using. I call them methods because based on my research, these were methods or functions in standalone libraries, but in the recent versions of Python, they are included into the string methods. Right? So these are the two methods we will be using. So to study that, I have the okay, I have 3 strings here. So string 1 will be S1, S2, and the test string. Basically, we will be mapping S1 to S2. So we will be substituting characters, or in other words, we will be mapping 2 strings, right? And we will be using this maketrans function to generate a table to do the translation work, and then we will be using this translate method to get the new characters for our 3rd string. We call it test. So what I can do here is, as I've told you earlier, these are string methods, so I will be assigning them to strings. So test is there, so I can say, okay, so test as my string, and I can do the make trans method, and I will be mapping S1 to S2, and I can assign it to my variable, and in this case I will call it translation table, because that really shows, if I can do the translation. Okay, here if I work on this, spelling error. Okay, well, so basically translation table is mapping the two strings together. So A has an ASCII code of 97 and E has an ASCII code of 101. So these are the ASCII codes mapped together, right? So this translation table is necessary for me to translate, let's call it test translate, I will be translating this test string using the translation table based on S1 and S2. So I can just take this translation table and put it over here. And if I do that, it will basically take individual characters here on the test string, starting with uppercase T, and go to the translation table, find the uppercase T on the string 1, and look at the corresponding character for uppercase 2 in string number 2 and return that value. Quick example. So if you look at this, this A character here, it is the third character on the last word, so it becomes E. So let's check it out. So if you look at this mapping here, A is mapped to E. So this A in here, the third character in the last word, is mapped to E. Right? This is how this works. So the reason I discussed about that is because we will be using this option for encoding and decoding. What we will do basically, we will let's say we will translate. So st is the argument here on this function. So st in these two sample texts, the tests, st will be this one in the first one, st will be this in the second one. So we will take the st and we will translate it, and to use it on the translation table, we will again be calling st maketrans, and this translation will be between English alphabet as in self A and the cipher or the encrypted alphabet in self B. So basically, this function will take the string st here and look at the letters in the English alphabet and find out the corresponding characters in the encrypted alphabet and then return that to us, right? So basically I need to put return so that this operation will have this return st as in here. So I can copy it and replace it with paste in such that I will be doing this decoding. So I think I should put S here, not B. I should be using the alphabet, the cipher encrypted alphabet, and change it to the plain alphabet. That should work. Let's give it a try. Okay, the first one did not work. Okay, I think I forgot to mention here, we are dealing with upper cases here all the time. So if you look at the output, in the second case, test passed because everything was in upper cases, so there's no need to worry about it. But in the first test, the letters, except for the first letter, they're all lower cases. So the way to fix that is I can probably put upper as a new argument. So we'll do the operation and then convert it to uppercase. All right, so I think I need to get rid of this here. Test it out. Worked. Go. Work. Okay. Well, that was quick. The maketrans and translation methods are really helping us to switch from plain text to encrypted text, or vice versa. And this here, the first initialization function, we have to define this plain text alphabet here, and also the what's that called, Caesar cipher. And Caesar cipher has a rule that every letter is shifted by an integer given on the function as an attribute. All right, thanks for your time.